So, thank you for your introduction. I hope I'm well understandable and that my slides are visible. Very good. I'm really impressed by all the presentations that I saw so far. I realized I don't have so many numbers in it as usual the presentations have. So I thought let's add a number. I think we started with 38 participants, and we are now at about 32 participants in the meeting. So we have a loss of 15%, so to say. So 1 dB loss. I don't think that is too bad for a communication link, so to say. I'm Rudolf Saathoff. I called my presentation Fundamental Challenges for Laser Satellite Communications and Quantum Key Distribution. We talk mostly about, or I talk mostly about the laser link between two communication terminals. I'm working about 6 years on laser satellite communications, 4.5 years at TNO, and I started in March at TU Delft as assistant professor. So I don't have extended research results, but I do want to share my vision on the challenges that we have. I also need to thank my colleagues, Stefanos Paretta, Jan Guo, Hans Kuiper, and Eberhard Gill, who contributed to the paper and also to the presentation. So first, a small introduction of the group I'm in. I'm from the aerospace engineering faculty. The group, or the departments of space engineering, and then the group or section of space systems engineering. And a couple of the things that this section did in the past is creating small spacecraft. The first one is the Delphi C3, which is a 3-unit CubeSat satellite, launched in 2008. Second one is the Delphi Next, launched in 2013. There's, for instance, some experimental payloads on board. Besides that, it's very small. That is a foil solar panel and also a wireless solar sensor for the orientation of the satellite. And one spacecraft that will be launched in 2022, it's already ready. It is mounted and ready for launch, is this Pocket Cube satellite. It has dimensions of 5 by 5 by 20 centimeters, so that is then called a 4-unit pocket cube. So our research in our group focuses on miniaturization, and then you can think of attitude control for small spacecraft, miniaturized instrumentation, and also we have a strong lag in propulsion. Also, we have research focused on distributed systems such as navigation and control and on-orbit surfacing. And we also do system engineering, for instance, for optical space instrumentation. So this is a little bit a close-up of the Pocket Cube. Here you see a cross-section. It's a photograph. And this kind of activity is for research purposes, but also for education purposes, like the integration, the testing, the engineering is all done by, to a large extent by students, but also by staff. So this is a little bit what we do. And also, we recently entered in the field of optical satellite communications. So that is both a ground to satellite and the other way around, of course, but also inter-satellite communications. And here I have a nice I have an animation on what happens with such a communication link. So first of all, the satellite is moving. And the idea is to point the laser beam very accurately towards the satellite. This is, for instance, very important when you do the acquisition phase, which is the handshake, so to say, between the ground terminal and the space terminal. So what you need for it is a good knowledge of the position of the spacecraft. Orbiting modeling is very important. But also what you can see is that the laser beam is not standing still, but it is moving around. This could be by two reasons. One is the turbulence. So what you see over here, this like simulates the turbulence or represents the turbulence. This can be a reason for the beam wander, but also the motion of the terminal itself. With the last presentation, one of the challenges mentioned was the motion of the aircraft. So this is something, this is an important challenge. One other challenge related is the clouds, because when there is a cloud between two terminals, it is not possible to have communication between them. Also, I almost forgot, is besides the beam wander effect, the clouds again, besides the beam wander effect by the turbulence, also what you can see in this animation is a speckle pattern. Basically, the Gaussian profile of the laser beam envelopes a certain speckle pattern. So if you look carefully, you see the speckle pattern moving with a kind of constant speed, which is proportional to the turbulence layer. And then it's overlapped. So you see the combination here of two effects in this spot, which is that of beam wander and also of scintillation, which is optical fluctuations or on axis. And this is caused by the constructive and destructive interference. And so if you probe the satellite with a photodiode, you will see the fluctuations both from the constructive and destructive interference, also called on-axis scintillation, and also by the beam wander itself. Then there's also a third atmospheric effect, and I represented it here by a cloud, but the laser beam needs to travel through the atmosphere, and this is attenuating the beam, and this is also called atmospheric extinction. So these challenges basically are to understand how much of these phenomena affect, so in the extent of, because one of the important points of because one of the important things of service providers is availability, and one of the topics that I'm interested in is to see how much availability you can have with still having these effects. So one other thing is, the sun. This plays, for instance, an important role for quantum key distribution links, because the sunlight is also entering the optical telescope or the ground station, or maybe a satellite terminal, and this is also falling on the detector, and then the single photons from the QKD process has to compete with photons that are coming from the source. So signal to noise ratio or filtering is also an important challenge to deal with. And then there is two other things that I don't have such a nice animation for, but that is, we've already seen also the presentation of Ersician and also TNO with the in-field demonstrations. I think it's also important, next to this nice in-field demonstration, also to have in-orbit demonstrations. And luckily, this is also coming in the next future. And also, we heard also stories about costs. This is a driver for low swap size, weight, and power. Because if you want to send a satellite or technology into orbit, you better take care that the weight is small and that this is also an efficient process. So very quickly, this is generally how an overview of systems architecture for space, but also maybe to a large extent for a ground terminal architecture. You have a course pointing mechanism to follow the satellite. There is a fast steering mirror to mitigate the fast fluctuations, the beam wonder and the beam jitter. A tracking controller to control both these stages. Of course, also the attitude control of the satellite itself need to be taken into account. Also a point ahead mirror. And there is also the other technologies like the transmitter and the receiver. And as you can see, I focus a lot on the optomechatronic challenges over here. But with the presentations of the others, you can see that there's a lot of other challenges and technologies that deserve focus. This is just some nice pictures from TNO from their existing hardware, and to also emphasize this again, it would be great. We have this technology to also work together to go one step further, go into in-orbit demonstrations and do it together with industry, with the academia, together with students, have nice learning goals, with nice research projects to make this happen. So within the optical wireless superhighways, there's also 3 PhD projects that will run in the future in our section. One is formation flying and satellite communications. Here you see 2 examples of a constellation, and one of my colleagues is especially interested in autonomous formation flying. So the processing and the control is done by the spacecraft itself and not by external control, for instance, from the ground. And as an aid, satellites, laser satellite communications can be used, for instance, for the distance and the orientation between the 2 spacecraft. And a science call can, for instance, be gravitational observations. One other, and I do not want to spoil too much because Joshua Stander will have a talk on this, is multi-beams terminals. This is a render from SES, where you can see the benefit, but you will hear more about it in the next talk. And one last topic, and also a new research project in this overall project is what you see here is deployable telescopes, a deployable telescope. This is to reduce swap size, weight, and power. So if you start with a small piece of equipment, you launch the equipment, and then in space you can deploy it. So there's all kinds of mechanisms that play here a role. For instance, the deployment mechanism. This is, for instance, a roller hinge. This is a photograph of it, so it is tested at the premises. You see in the design, it sits over here. And this is the support of the first mirror of such an element over here. And this is for precise positioning of these elements, which basically comes to the conclusion of my talk. The takeaway message is I do just the headlines here because I ran out of time. TU Delft Aerospace Engineering is joining the laser satellite communications. We have new PhD projects on optical wireless superhighways. I told you a little bit about, or I told you to a large extent, actually, for future challenges that I think are a challenge for laser communication links. And I also linked a little bit towards that there is other uses for this hardware, for instance, for laser satellite ranging, formation flying, and space situational awareness. Thank you for your attention.